Thanks, Veronica. I'm excited. I know you are too. I was already excited when I got here. And then sitting through the mission briefing this morning, I'm even more excited than I was before. How exciting. 5 more days and we'll be there. We'll be landing yet another planetary mission on the surface of Mars. Each of the planetary missions, each of NASA's planetary missions, is on a quest to answer important questions about how our solar system formed and how it changed over time after it formed. We've sent lots of different missions to different worlds and different corners of the solar system, and they're each trying to answer that same question in different ways, different types of observations at different types of worlds. Some of the most fundamental questions that we have about how our solar system formed and how it evolved have to do with how did the rocky planets in our solar system form and evolve. The rocky planets, Mercury, Venus, Earth, Mars, and even our moon. Each of them are similar. They're rocky planets. Some of them have atmospheres, and they have structures that are similar, have similarities and differences. If I could have the first graphic, this graphic actually shows a cutaway of Earth and Mars and the moon. And what you can see inside of each of these rocky planets is that they have at their center a core. And that core can be solid or it can be molten. And then outside of that core, there's a middle section that we call the mantle, which makes up the bulk, most of the mass of each of the rocky planets. And each of those rocky planets is covered with a thin crust. What we really want to know is what are the similarities? How are they different? How are they the same? What are the relative sizes of those different parts of the interiors of those rocky planets? The different sizes. Is the core, is it molten or is it solid? Is that the same for each of the planets? That we need to know. Most of the missions we've already sent to Mars are either making observations from orbit, getting at the surface conditions, trying to understand what's happening within the atmosphere on the surface, sending landers and rovers, again, just scratching at the surface to understand that surface environment. If we want to understand what the insides of these rocky planets are like, we have to make different kinds of observations that can really penetrate down into the center of the planets. The types of measurements we make on Earth are things like seismic measurements, understanding the level of seismic activity, thermal measurements, heat flow, understanding the amount of heat that's getting out and released from the planet. We do this on Earth on a regular basis. We've actually even done these types of measurements on the moon. With the Apollo program, we had astronauts that brought these types of experiments and deployed them on the surface of the moon. But if we want to make these kind of measurements at Mars, we haven't sent astronauts to Mars yet. They will be going at some point in the future, and a lot of what we're doing is in preparation for that. But if we want to do this on Mars today, we have to do it robotically. And so with that, I'm going to introduce Dr. Bruce Bannert, the PI for the InSight mission, to tell us a lot about the science. And when I go off the stage, I just want to say, go InSight. Yeah.
Okay, so InSight is going to Mars to study the deep interior of Mars in order to understand how all the planets formed. I mean, we know a little bit about how planets form. They accrete from a solar nebula. As they accrete, they get hotter and hotter, both from the energy of the impacts and from radioactive decay. And then they melt and transform from sort of a uniform ball of meteoritic material into the diverse planets that we see today. Some of those planets are a little bit harsh. Venus is hot enough to melt lead. Mercury has a sun-baked surface. Mars is pretty cold today, but Earth is a nice place to take a vacation. So we really like to know why one planet goes one way, another planet goes another way. And those answers are in the details of the structure that's formed very early in the planet's history. On Mars, that structure's been preserved for over the last 4.5 billion years, whereas on the Earth, where we actually can study it pretty easily, that structure has all been sort of scrambled up, both by plate tectonics, by mantle convection, and so the evidence of the very earliest processes has been wiped away on the Earth. We want to go to Mars to do that, to study those processes, to look at how those processes came about very early in the planet's history. The main way that we're going to do that is with seismology. And the way we use seismology, when you want to study something, the first thing you want to do is look at it. And the way you look at it is you bounce light off of it, it goes into your eyes, and your brain can interpret it as an image and see a 3D image of what you're looking at. If you're looking at the center of a planet, light doesn't help you very much because it doesn't go very far through rock. So what we do is we use seismic waves, vibrations that are created by earthquakes on the Earth, Marsquakes on Mars, also meteorite strikes. Anything that starts the planet vibrating sends those waves through the planet. If I can have the first animation. This shows a seismic event on a planet, and it's showing the waves that travel through the planet, the blue P waves, the red S waves, and these waves travel through the planet the same way light would travel through a lens or something like that. And so a Marsquake is sort of like a flashbulb that goes off and illuminates the inside of a planet, and our seismometer is the eye that we use to see what's inside the planet. And by looking at those seismograms that you've seen on television, those wiggles on a graph, scientists have learned how to interpret the shape of those waves, the time which they come in order to understand the medium through which those waves travel. We can figure out what the inside of the planet's made out of. We can figure out where the different boundaries are between the rocky mantle, the iron core, and so forth. And so a seismometer allows us to look deep into the planet and understand the detailed structure. We also have a few other instruments, a few other investigations on this mission. One is a radio tracking experiment. We actually track the planet very precisely. And in particular, we're tracking the North Pole of the planet and watching it wobble as the planet rotates. And the wobble at North Pole is tied to the interaction between the planet and its core. And by looking at the wobble, its size, its frequency, how fast it's wobbling, we can actually determine the size of the core and what it's made out of. And that's very critical in terms of understanding the history of the planet and the way the planet is operating today. And finally, we have a heat flow probe. It's a very interesting device. Tilman Schwann's going to tell us a little bit more about it later. It penetrates down into below the surface, about 10 to 15 feet below the surface, and measures the temperature as you go down, and we're able to use that to extrapolate to the center of the planet and understand how hot it is in the middle of the planet and how much heat is coming out of the planet. And that heat is what actually drives the geology at the surface. And in particular, it drives tectonics, which is the quake motion of the planet, and it drives volcanism. And here to talk a little bit more about these geological processes and how InSight's going to illuminate that is my deputy PI, Susan McCarr from JPL.
All right, thanks, Bruce.
Thank
you. All right, well, every geologist and geophysicist that I know likes to climb mountains. And if we could have the first graphic. Most of us aren't lucky enough to be able to climb Mount Everest. However, some of us are privileged to be able to study the mountains on Mars. And as you can see, the mountains on Mars actually dwarf Mount Everest. These volcanoes are not only the tallest mountains, but they're the tallest volcanoes in our solar system. These volcanoes actually formed billions of years ago on Mars, and when they formed on Mars, they actually covered about a quarter of the planet. You can see Olympus right here, and you can see this whole volcanic region that formed early in the history of Mars. And if we go to the next graphic, we can talk about how these volcanoes formed. For me, really the most compelling thing about volcanoes is the fact that they are really conduits from material way deep in the planet to the surface. Not only do volcanoes spew lava on the surface, they also release gases into the atmosphere. They release things like water vapor, carbon dioxide, methane, all the things that we need to actually form an atmosphere. So the best analogy between the volcanoes on Mars and those we have on Earth are actually places like Hawaii. So Hawaii is an example of a hotspot volcano. So material from deep in the mantle, actually at the core mantle boundary, rises up in a plume over tens of millions of years And as they come up and intersect with the crust, it forms volcanism at the surface. It actually is intersecting a conveyor belt. The plates are moving slowly across that plume, and so one volcano forms and it's carried off downstream. So actually at Hawaii, there's when we see those few volcanoes at the surface now above the ocean, but it really is just one of a series of volcanoes, dozens and dozens of volcanoes that are now under the surface of the ocean. On Mars, we don't have plate tectonics. So when that plume comes up and hits the crust, it stays there in one place. And so instead of making a line of volcanoes, we have a series of volcanoes. And you can see this complex of volcanoes that was formed above a mantle plume early in Mars's history. The thing that we're really looking forward to for InSight is being able to go back in time. Mars formed these volcanoes in its first couple billions of years at a time when there was a magnetic field, when there was liquid water in the surface, all conditions that we think are important for habitability of a planet. For InSight, we're going to learn about the interior structure, the core, the crust, the mantle, the heat sources in the interior. And with that information, we'll be able to better understand how the interior of the planet affects the surface environment on rocky bodies, not only on Mars, but in our solar system and on other rocky bodies around other stars. I personally have been waiting for this information for decades, and I'm super excited to start getting this lander on the ground and start taking this data. Up next to tell you about some of the instruments that will acquire this data for us is Philippe Laudet, and he'll be telling us about the SEIS instrument. All right.
Okay. Good morning. My name is Philippe Laudet. I'm working for the French Space Agency, which is called CNES, so sorry for my French accent. And I have been the project manager of the SEIS instrument for now more than 7 years, since the pre-selection of the Discovery program in 2011. So as you have understood, InSight will make measurements of quakes and meteorite strikes on the surface of Mars, and for that he will use a seismometer SEIS, which is provided by the French Space Agency CNES, and also by IPGP, with a French laboratory for geophysics research, and it's our French PI for SEIS, Mr. Philippe Laudet. And as you can see, I don't know where the film is. Oh, sorry, I didn't see the screen. Thank you. So this instrument will be deployed exactly on the surface of Mars in order to have better accurate measurements of the seismic waves. And the major engineering challenge we had due to that position on the surface is to protect the instrument from thermal variations and also from the wind of Mars, which is very aggressive for that kind of instruments. So you have a protection on the seismometer itself, and another one is the wind and thermal shield, which is being deployed on the film, which is deployed in a second time by the same robotic arm, exactly on the seismometer. And there is absolutely no mechanical contact between both, because the windshield will move with the wind, but not the seismometer, of course. Okay, and as you know also, we are not the only instrument on the surface. We have another one, which is a German one, HP Cube. And I leave the floor to Tilman Spahn, who is going to talk about HP Cube. And I tell you goodbye, thank you, and see you on Mars next week. Bye-bye.
Hi, greetings from Germany. I'm Tilman Spahn from the German Aerospace Center, DLR, and I'm the lead of the heat flow probe, the HP Cubed experiment. DLR has been building this instrument and contributed that to the mission. Now, as Prue's already told you, we're taking a set of temperature sensors down to a depth of 10 to 15 feet to measure the temperature and the heat that is coming from the interior towards the surface. Now, how are we going down? Let's play my first animation. Can we have the first animation, please? Okay, here is the winding mechanism in the mole. We nicknamed that penetrator a mole that compresses the spring. And when the spring is released, it hammers, towards the tip of the mole and then propels it down into the ground. Now we stop the penetration at about 2 feet and take a measurement of the thermal conductivity. And then we continue that. Let's continue the animation. Can you continue, please? And we take we heat the mole and measure the thermal conductivity, and then we continue the penetration and take another measurement of the thermal conductivity and another measurement until we get to the target depth of 15 feet. When we're down there, we will then we'll then activate the temperature sensors, 15 temperature sensors that measure the temperature profile down to a depth of 15 feet. And by combining the temperature increase with the thermal conductivity, we can actually calculate the heat flow. Now, I'm very excited to come here on Friday and then attend the landing event. And then, of course, the experiment, the penetration first, and then the measurement of the temperature and the thermal conductivity and the heat flow, because that will help us decipher, the energetics or the activity of the planet. And this is something that geophysicists have been looking forward, for a very long time. And with that, I'd like to hand back to Veronica to continue the presentation. Thank you very much for your attention.
All right, thank you so much, and stay where you are, Tillman. We're going to bring the rest of the panel back up on stage now to do some questions and answers. A reminder that we will take questions here in the room. We have some media on the phone line. If you're on the phone line, please hit *1. That will put you into the queue for a question. We're also taking questions on social media. Just use #AskNASA and send those in to us. We'll take some during the broadcast. We'll continue to answer those even after we go off the air today. So we're going to open it up here first in the auditorium, and then we'll go probably to phone lines next. So go ahead.
Hi, Ryan Blackshear-Vargas again from Spectrum News. You mentioned there's lots of questions that will be answered. What's the #1 question you want answered after 2 years?
I think the #1 question we want to answer is what's the structure and the energetics of the interior of Mars. And so we have several things that we want to measure. We want to measure the thickness of the crust, the size of the core, the density of the core, and the seismic velocity of the mantle, which tells us sort of what the structure of the mantle is. And those are kind of our key questions, as well as the amount of heat coming out of the planet. So when we proposed this mission 8 years ago, we put together what we call our level 1 science requirements. And these are the things that sort of we promised NASA that if you choose our mission, these are the things that we're going to measure. And that's kind of our list of measurements. And then we also are going to measure how often Marsquakes occur, and how often meteorites strike Mars, which is kind of a bonus.
And then a follow-up question, how does all of this help us understand life here on Earth? Will we understand better earthquakes? Will we understand volcanoes better? Will we understand, what kind of everyday parts of our life here will the InSight mission help us understand?
Well, what it really helps us understand is how we got to where we are today. How we got to an Earth that has an atmosphere which is breathable, an environment which is in a temperature range which is comfortable for life, how we have a planet that's covered with water. These are all things that are related to the activity and the structure of the inside of our planet. It's not obvious to everybody, but the fact that we have an atmosphere is because we've had all these gases that have come out of the inside of the planet. The reason we have ocean is because the water has come out from volcanic activity over the billions of years. And so that activity is tied to the initial conditions of the planet. And so we'd like to understand how that happened, how we got to where we are today.
Thank you.
Yeah, and if I could just add to that, life started on Earth, we think, very early on in the first 500 million years, and that crust is almost gone on the surface from the surface of the Earth. Whereas on Mars, that very early crust is still preserved. Those environments that it formed super early in the formation of planets, of our solar system, and so we can kind of go back in time and study those environments on the surface of Mars and understand how the conditions inside the planet created those environments.
Thank you.
Okay, we're going to take one more here in the auditorium, and then I'm going to go to the phone lines, and then we'll be coming back.
Hi, Ian O'Neill for Scientific American and HowStuffWorks.com. Going back even further than that question, how does your assembly of instruments and experiments help explain the origins of planets themselves? I mean, was it, it's almost like a time probe looking back over 4 billion years ago, but how do you hope this will add pieces to that puzzle?
Well, as you said, the structure of the planet is really formed in the first few tens of millions of years after the planet accretes. So we're not going to have much to say about how the planet actually accreted. But once it gets formed from the solar nebula, how it changes from sort of a uniform ball of meteoritic material, which is all kind of the same stuff, into a planet which is differentiated, which has a crust of relatively light rocks, and a very dense core, and a very complex system of transferring the heat from the center of the planet to the surface. These things are all kind of set up very early in the planet's history, and for the Earth, we don't really have any evidence of that system left anymore. What we have is a very evolved system, and so we want to go to Mars to see what that system looked like very early in the process, and so to better understand the physics and the chemistry of how you go from the very initial set of conditions with this sort of solar dust and ice that's accreted into the very complex planets that we see today.
And just one follow-up. In regards to meteorite impacts, how many meteorite impacts do you expect to detect with your instrumentation? And yeah, that's the question.
Well, one of the things that we want to actually find out is actually measure how many. We're sort of expecting something of the order of maybe a half a dozen to a couple of dozen in the 2 years that we're on Mars.
Cool. Thank you so much.
Sure.
Okay, we're going to the phone lines next. We've got about 3 different callers right now. We're going to start with the AP. Go ahead.
Yes, hi. This is Marcia Dine, AP. I have a question I'd like both Philippe and Tillman to answer. NASA has a long and rich history of exploring Mars, and as the relative newcomers to this, I'd like to know from both of you what you find so captivating and magical about Mars versus other planets.
I don't catch everything. Could you repeat to me?
She wants to know what you find fascinating and captivating about us going to Mars and studying Mars.
Everything is captivating first. It's a dream first, and after there is a big challenge because that instrument was supposed to be so sensitive that at the beginning it was just impossible to build. Okay, but we did it with the help of our partners, and particularly JPL. Thanks for that.
Would Tillman like to also weigh in?
Okay, to me, Mars is a planet that is, on the one hand, very different from the Earth. On the other hand, it's quite similar. It's half the size of the Earth, but its environment on the surface is, more Earth-like than, for instance, the atmosphere and the environment of Venus. And understanding the difference between the Earth and Mars, will help us understand the evolution of terrestrial planets in general, and in particular the Earth. And this is what, makes the motivation for going to Mars. And in addition to that, it's easier to explore Mars, than Venus. And therefore Mars is the first target, to do a geophysical observatory like we now do on Mars. So it's timely, and it's very much, justified to do that now.
Okay, our next question on the phone line is from AFP. Go ahead, please.
Hi,
Hi, this is Ivan Kron of Agence France Presse. You mentioned Mars quakes and meteorite strikes. Can you talk in details about the other possible sources of vibrations that you might listen to?
Sure. So those are the two primary sources of vibrations that we hope to see. We also actually will probably see vibrations due to the interaction of the atmosphere with the surface. So when you have weather on Mars, you have turbulence, that actually is pushing the surface up and down. That will create, on one hand, it creates noise that makes it harder to see the Mars quakes, but on the other hand, when you start beating on a planet like that, it'll actually start resonating at certain frequencies, and those resonances are affected by the structure of the planet, and so we may actually be able to get some information from that. And finally, what we should also be able to measure is actually this is not exactly a vibration, but it's the motion of the surface up and down due to the tidal pull of the Martian moon Phobos. And so every time Phobos goes overhead, it actually pulls the surface up a little bit, and then it goes back down after Phobos leaves. And so we can actually measure that. It goes about a centimeter and a half, a little over half an inch up and down when Phobos goes over. And it turns out that we can actually use that measurement as well to look at the inside of the planet, because how much that goes up and down depends on sort of the elasticity of the planet and whether the core is solid or liquid. And so we'll be able to use that measurement as it happens every 7 hours or so on Mars to probe the inside of the planet.
And if I may, could there be some magma movement at all from the inside?
There could be magma motion on Mars. The area that we're landing in is pretty featureless. I mean, it was a lava plain, but it was put down, several billion years ago. So we're not expecting any active volcanic activity in our region. It's possible that it could be happening somewhere else on Mars. It's conceivable that we could pick that up with our seismic instruments, but we're not expecting it.
Yeah, but we are in a good place. It's about 1,000 kilometers to an area that may have been volcanically active in the last 10 million years. So for Mars, that's yesterday. So we can hope that we might hear some magma deep under the ground, not at the surface, but deep underground.
Yeah.
Thank you.
Okay, we're taking one more from the phone line, and then we'll come back into the room. We're going now to space.com. Go ahead.
Thanks for taking my question. This is Megan Bartels from Space.com. I had a question for Lori. I was hoping you could talk sort of big picture. Why is it that we're so fascinated with Mars and we keep returning with science missions? What is it that really captures us about the planet?
It's a great question, and Mars is an incredible natural laboratory right next door to Earth. And as I was kind of alluding to at the beginning, we really want to understand how we came up with this diversity of rocky planets in our solar system. They're all very different. Each one of them is unique in its own way, and trying to understand how they ended up so differently is a really important question. And Mars is a great natural laboratory. It's right there. It's reasonably easy to get to. We demonstrated that we can land successfully on the surface. We can conduct scientific experiments for long durations on the surface. So it's very amenable to trying to do these types of investigations. And then in addition to that, Mars has another piece of intrigue for us in that it could have potentially had a significant amount of water there in the past. We see lots of evidence of that in the geology. And so we do believe that there was a lot of water there, and it could have potentially been a place where life could have formed very early in Mars's history. And of course, trying to understand how life is or was distributed across our solar system is one of the major questions that we have. Are we alone? Were we alone sometime in the past? And so Mars is really an intriguing destination for that purpose as well, trying to really understand what those conditions were like back 4 billion years ago. Did life actually begin on Mars in that time frame? And if it did, is there any preservation of that left on the surface? Of course, that's not the focus of the InSight mission, but it is the focus of a lot of the other investigations that we're interested in at Mars. And so trying to better understand Mars in that context is important. And then finally, as was alluded to this morning in the mission briefing by Dr. Zabukin, we'd like to eventually get humans back to Mars. We're interested in a campaign now in returning humans to the moon and eventually getting humans to Mars. Again, another destination in our solar system where we feel it is amenable to human exploration and a place where we could go at some point in the future. And science drives our understanding that allows us to get humans to a place like Mars. And so the more exploration we have, the better we understand that environment, the better prepared we'll be to send humans to Mars in the future.
Great. Thanks so much.
Okay, we're going to bring it back into the room here for questions from media, and then from social media, I see our team over here working furiously collecting your questions, so stand by for that. Go ahead with your question.
Hey, Charlie Shelton with CV Weekly. I have a question about the Olympus Mons formation. What is it that is different between Earth and Mars about tectonic motion? Why do the plates not move and allow something so big to build up?
Yeah, so I mean, that's part of what we hope to learn from this mission. In fact, for the first order answer is that Mars is a lot smaller than the Earth, and so it doesn't have the same amount of radiogenic material, the same amount of heat that it starts out. So just being a smaller planet, it loses its heat more rapidly. So, you need to have a vigorous convection, a lot of energy inside the planet to drive that motion of plate tectonics. People have proposed in the past that maybe very early in Mars's history it had plate tectonics. Now, we don't have any direct evidence of that. And we don't expect to see evidence of that on Mars with our mission. But it's always the things that we don't expect that turn out to be the most intriguing. So who knows what we'll find in the interior.
Follow up to that, is there any way to tell either from aerial view or a mission like this, maybe in a different area, if there is a previously active subduction zone or any of those other things, or can you tell even where any of the transform faults are? People had proposed that there might have been subduction and transform. We do see evidence for transform faults from the high resolution topography data that we have. And in the past, people had proposed that there might be subduction zones on Mars. We think that that's not the leading hypothesis for how the northern plains formed. It was previously proposed as an option for how that low topography in the northern hemisphere formed. We now think it's likely due to the presence of a huge impact early in Mars's history. And we've come to that hypothesis based on the topography, the gravity data, the geology and the faults that we see at the surface. InSight will actually be adding to our knowledge of how these two hemispheres formed. We'll be understanding the thickness of the crust, which we don't know very well at all now. We'll see perhaps if there's a difference in the composition and the thickness. We know there's a thickness difference between the north and south, but getting the exact difference between those two will help us better interpret these hypotheses. And we assume it's going to support the impact theory, but again, we'll find out. Thank you.
All right, we're taking a question right here. Go ahead.
Hello. Steve Gorman from Reuters. So two questions. One, how long after the InSight lands, if it arrives safely and settles safely, will it begin to conduct, will the seismometer and the heat probe begin to do its things? And then also a very specific question about the sensitivity of the seismometer. I believe you said in the past, Dr. Brenner, that it would measure seismic waves as small as the diameter or half the diameter or half the radius of a hydrogen atom. Could you give me that one more time?
Yeah, that's right. I mean, the sensitivity of the seismometer is in acceleration units. Our requirement is 10 to the minus 9 meters per second squared, and if you turn that into displacement, that comes down to less than 10 to the minus 10, which, if you, depending on exactly how you define it, it's about half the radius of a hydrogen atom. And that's
radius.
Yes, and we're actually a little bit better than that over part of the frequency band. Thank you very much, Philippe. We're about a factor of 5 better than that in some parts of the frequency. So yes, we're pretty doggone sensitive. And so one of the issues that gives us is that makes us sensitive to everything else that's happening in our environment. You know, if there's a little bit of wind, if the temperature changes a little bit, even if a little pressure front goes by, it's going to change the seismometer around. And so that's why we have a weather station on board, which we haven't talked about. Our core mission, but we have a very competent weather station. It's going to give us temperature, wind, and barometric pressure 24 and a half hours a day, every day on Mars. And so, in addition to doing all this science about the deep interior of Mars, we're actually going to be contributing a lot to understanding the environment, the surface environment of Mars as well. And okay, so in terms of how long it's going to take to get the instruments going, InSight's kind of a laid-back, slow-motion mission compared to a lot of things that we've done before. We have a 2-year mission to do our science, and so to get that mission started, we have to get our instruments on the ground. It's going to take us about probably 2 or 3 months at least to get our instruments down. And that's because we have to do a survey of the area in front of the spacecraft, make sure that we don't put the instruments down on a rock or in a hole or something like that. And then we're very, very, very careful about how we put the instruments down. You saw the animation that they had the robotic arm going and picking up the instruments and putting them down. It actually goes a lot more slowly than that, and we have a whole set of activities that we go through to ensure that when we put those instruments on the ground, they're going to be in a place where they can operate properly and get these kinds of measurements. So it's going to take us, probably a month or two to get the seismometer down, and another month or so to get the heat flow probe down and penetrating down into the surface. So whereas we're going to get some photos and some preliminary data back before that, in order to really get operating, we're probably looking at early next spring when we're really going to start bringing back that kind of science from Mars.
Thank you.
Okay, we're going to turn it over to the social media team to tell us some of the questions that have been sent in.
Well, Bruce anticipated one of the hottest questions out there that everyone was asking us, how long until we get the data? And you mentioned the cameras. Desvain on Twitter asked, does InSight take pictures? And if so, will we be able to see them?
It does take pictures, and you will definitely be able to see them. We have 2 cameras on board. We have one's called our instrument context camera, and that's going to take a picture just a few minutes after landing. And it's bolted to the bottom of our deck, and it has a fisheye view, so it's going to show about 120 degrees, 130 degrees of view just right in front of the lander, perhaps even up a little bit above the horizon, down to very close down to the spacecraft. And that shows the entire area that we're going to be trying to map out to deploy our instruments on. Then we also have another camera. It's actually attached to the robotic arm. It's a higher resolution camera, and we use the arm itself to point that camera, and we're going to be able to put together mosaics of both the area in front of the spacecraft and the entire region around the spacecraft. And those images are going to go out onto the internet more or less right away as soon as we get them. So we'll have raw images out on the internet for people to look at as the mission progresses.
Fantastic. Okay, so Winter in our YouTube chat wants to know, how will the InSight seismometer be able to map the internal structure of Mars in 3D with just one sensor? How is that accomplished? And Rabbi Cooper over on Twitter follows up, don't we need 2 or 3 to determine the inner composition?
You would think, wouldn't you? Usually if anybody knows anything about seismology, you know that you need at least 3 seismometers to do seismology. And that's true unless you get really clever about it. So we had to get clever. I mean, we actually had lots of concepts of missions that had 3 landers, 4 landers. We even had a concept with 18 landers on Mars at one time. And none of those actually ever got funded because they're very expensive. And so we had to go back to the drawing board and figure out, well, how can you do seismology, real quantitative seismology with a single seismometer? And it turns out there are quite a few techniques that are available to us. I mean, and people have used this on the Earth, but they get sort of eclipsed by the sort of array seismology that we normally do. And one of the things we do on Mars is we use the fact that Mars is small to our advantage. And what happens is that in addition to the P waves and the S waves that you normally hear about in seismology, there's also something called a surface wave, and that's a separate kind of wave that travels along the surface of the planet. And so, in addition to the P and the S wave, we actually get the surface wave, which travels to the seismometer. And there's another one that goes the other way around the planet and comes in the long way. And so there's two extra, what we call arrivals. And then finally, the one that's gone all the way around the planet can go around again and hit our seismometer. And these things can keep going around. They get a little bit smaller and smaller each time, obviously. So we use that extra information to be able to figure out how far away the Mars quake is, and we can actually use what's called polarization analysis to figure out which direction it's coming from. And so instead of having to triangulate on it using multiple seismometers, we're actually able to use sort of the extra information that's contained sort of later on in the seismogram in order to get the distance and the direction. And it gets more complicated than that, but that's sort of the basic method.
We've got a mountain of questions, Veronica. How much time do we have?
I think we're good. Go one more, and then I'll do a final look in the room here to see if there's other questions. Go ahead.
Okay, well, two-parter. Okay, Oscar wants to know, is there an opportunity for citizen science to participate with this mission?
Well, we will be putting the seismic data out on the internet within a few months after acquisition. If you're a citizen seismologist, you can certainly work on it. We'll also be putting the images out, and there's a very vigorous community of photo interpreters out there that have been doing photo interpretation on Mars images for many, many years, and our images will be available for that as well. We also have something called seismometers in the schools, and we're actually going to be sending the seismic data out to schools which are participating in our program at the same time, basically, that our scientists on our team are going to get it. And so the students at various middle schools and high schools are going to be our data in close to real time, and they'll be able to try their own interpretations on it and so forth. And we're hoping that they don't beat us to the punch in any of the big discoveries, but we'll see what happens.
And additionally, we have a Mars weather service, so you can get information about the weather daily at our site. You can get wind, atmospheric temperature, surface temperature. So you'll also get a daily weather report from our site.
Okay, let me ask one more time out here in the audience. Yes, we do have a question here. We'll get you a microphone.
Scott Sullivan from the Weather Network. I'm really interested in knowing about the weather on Mars. So this, as far as I understand, is the very first continuous weather monitor that we put on Mars. Previous missions have had weather, but it's very distinct measurements every day. This is going to be, as you said, 24 and a half hours every day. Do you anticipate learning anything really new about Mars weather that we didn't know about before?
The short answer is yes. I don't know what it is. We'll have to discover it. But yes, I mean, every time we go to a planet and look at something differently with a different set of instruments in a different way, we always discover something new. And this is, as you said, this is going to be a unique data set of continuous measurements, temperature, barometric pressure, wind, speed and direction, all day long, all night, over an entire Mars season. And that's obviously going to, I think, just have an enormous wealth of scientific information for us.
Okay, we're going to take one more social media question, and a reminder that if you have sent in a question with hashtag AskNASA, we'll continue to answer those after we go off the air. Go ahead, Stephanie.
All right, so this is for all of our scientists here today. Anna M. on YouTube would like to know, what would be more exciting for you? A result that meets your expectations or something completely unexpected?
That's an easy one. Unexpected is always a lot more fun. Yeah.
I would agree with that.
Yeah. Meeting your expectations is, gives you a nice warm feeling, and then you say, well, what's next? What am I going to do next? If you see something that's unexpected, that always opens up a whole new doorway into something that you never thought of before, and that's that's what a scientist lives for, really.
Exactly. Yeah, that's the coolest part. What we don't know now is what is the coolest part.
I was just going to say, that's what we do as explorers, right? That's why we're here. That's why we're doing what we do, is to find those unexpected treasures that are out there, the new discoveries that are going to drive the next mission and send us to the next destination.
Oh, yeah. The root motivation is exactly what they said. I have nothing to add, except perhaps one point to precise that there is a technological things, there is the challenge of the science discovery that we are going to make, and also there was a very interesting thing during all development, and also the following is to work together with different culture, different languages, different money, and it's definitely very interesting that people on Earth are able to work together before we wanted to talk with Martians, for example.
Okay, that concludes our briefing for today. Thank you all so much for spending time here. Thank you, Tillman, for joining us all the way from Germany. We look forward to having you out here for landing.
I'll be coming on Friday.
Okay. Now, I want to remind you about all the different activities we've got going on up through landing. So to watch our schedule on Sunday, which will be our final mission news conference before landing, and then also that afternoon we have a NASA social program that will also be televised on NASA TV. So we have the news briefing at 10 a.m. Pacific time, 1 p.m. Eastern time, followed by the NASA social event, which again is a great Q&A, another opportunity like this to send in more questions. That will be at 1 p.m. Pacific time, 4 p.m. Eastern time. And then landing day itself, Monday, November 26th. We want you to join us. The landing itself takes place about noon Pacific time, 3 p.m. Eastern. Our commentary begins 1 hour prior to that. And there are multiple ways that you can watch. The easiest way is nasa.gov/live. Bookmark that now so you have it for Monday. You're going to be online Monday anyways for Cyber Monday. You're going to be shopping. Just have that extra screen open. We also have a very good toolkit with a lot of in-depth information about the mission, a lot of fact sheets, and a very good list of multiple ways you can watch. That URL is go.nasa.gov/InSight Toolkit. There's great tabs there. You want to click on Watch Online. You will get a full list of all the different platforms where you can watch our broadcast, including our 360-degree camera from inside Mission Control. And you will also find on that site a tab that says Watch in Person. That includes a long list of public viewing events across the country. You've got viewing events from here in Los Angeles at Caltech and the California Science Center all the way across the country to New York, in Times Square on the NASDAQ Tower, and all the way into Europe. So please do go to that site if you want to join into a real conversation about landing. Do that, and we look forward to having you back here on Sunday for the news briefing and Monday for landing. And as we go into this Thanksgiving holiday for the in the United States, I just want to wish everyone a very safe and happy Thanksgiving, and thank you again for joining us. We'll see you on Sunday.